All right, so let's move into multi-digit multiplication and some of the algorithms that we're going to see being used when it comes to multiplying these numbers together. So what you are probably most familiar with is taking a number, a multiplication like 3 times 13, and aligning it one on top of the other. And then a pretty common way of doing a multiplication like this is that the student would say, okay, well, 3 times 3 is 9, so I put a 9 here. 3 times 1 is 3, so I put a 3 here. That is efficient and it gets things done quickly, but it doesn't really explain what's happening in the numbers. So when we do 3 times 13, I want to encourage you to think about this as 3 times 1 10 and 3 ones, because that's how that number can be broken down into place value. So now I can think about this as 3 times 10 using the distributive property plus 3 times 3. And this explains where I get 30 from, 3 tens, and where I get 9 ones from. So that's 39. So we can see we're getting the same response, but explaining it a little more using place value. So I could go through this algorithm to emphasize place value by saying something like, well, 3 ones times 3 ones is 9 ones, so I have 9 ones in my final result. 3 ones times 1 10 is 3 tens, so I put 3 tens in my final result. This is known as partial products typically, and we might write it something like 13 times 3 is 3 times 3 is 9, 3 times 10 is 30, and I could sum those things together as 39. So again, 9 came from 3 ones times 3 ones, and 30 came from 3 times 10. And that's called partial products. And this is, up here, this is more what we would call our standard algorithm. Now, we can visualize this using our array or area models and thinking about splitting our tens and our ones up from each other. So 3 rows of 10 bars, that gives us 30, and 3 ones gives us 9. All right, so I want to go through a similar problem, but this time it's going to require us to think about regrouping like we did with addition and subtraction. So again, our standard algorithm would tell us to say 16 times 4. 4 times 6 is 24, so I put a 2 up here and put a 4 down here. Then I say 4 times 1 is 4, plus 2 is 6. So I get 64. Now, everything I just did is because I've memorized that that's the way it's supposed to go. But learning to multiply this way can be quite difficult, because then you get questions like, okay, well, why did I multiply when I did 4 times 1, but then I added the 2? Why am I adding when I'm doing multiplication? And then students can get confused because they're just trying to remember the steps instead of understand what they're doing with place value. So what partial products algorithm would do is it would break 16 down into 10 plus 6 times 4. And that would leave us with 10 times 4 plus 6 times 4. And 10 times 4 is 40, and 6 times 4 is 24. So I have a total of 64, which gives us the same result. We could also write this in the vertical format by saying, okay, 4 times 6 is 24. 4 times 10 is 40. And I add them together. So I have 4 ones and 6 tens, or 64. We, in some cases, might need to multiply by 10 or some multiple of 10. So we can replace units with longs, replace longs with flats. So for example, if I needed to multiply 23 times 10, I would replace all of my longs with the flats and all of my units with longs. So I would see that 23 times 10 is 230. All right, so here's another example of how we can use that expanded addition or partial products method. So again, if we have 4 times 367, that is the same thing as doing 4 times 3 hundredths, or 3 times 10 squared, plus 6 times 10, plus 7, because we have 3 hundredths, 6 tenths, and 7 ones. So 4 times 3 hundredths gives us, or 4 times 10 squared is 12 times 10 squared, or 1200. And then 4 times 6 tenths is the same thing as 4 times 6 times 10, or 240. And 4 times 7 gives us 28. So in the written out like this, we would have 28 coming from our 4 times 7, 240 coming from our 4 times 60, and 1200 coming from our 4 times 300. Okay, let's look at one more example where we have, instead of multiplying with a 1-digit factor, we have 2 2-digit factors. So in this multiplication, we have 23 times 14. Now, I would say we can think about this as 20 plus 3 times 14, or 10 plus 4. Then we can go through and use that double distribution to see that first 20 times 10 plus 20 times 4 plus 3 times 10 plus 3 times 4. We can also think about this using a model. So 23 times 14 would be a length of 23 on one side, so 23 times 14 on the other. So we have a 10 and a 4. So when I think about splitting this up, I get 4 different quadrants with 20 times 10, 20 times 4, 3 times 10, and 3 times 4, just like in the multiplication I had with the double distribution below. And then I can simplify each of these components of my sum. So 20 times 10 is 200, plus 20 times 4 is 80, plus 3 times 10 is 30, plus 3 times 4 is 12. So that gives me 200 plus 80 plus 30 is 110 plus 12. That's 310 plus 12 is 322. So with that same multiplication, I could think of it with the base 10 blocks using a similar area model where I have 20 or 2 of my 10s and 3 1s as my number of columns, and 10 10s and 4 1s, and I can see the 4 different portions of this multiplication if I split it up this way. So 20 times 10, 20 times 4, 3 times 10, and 3 times 4. I could break it down and write out each of the partial products here. So 3 times 4, 20 times 4, 3 times 10 and 20 times 10. And together I get 322.